Here's an example. Here's an odd-looking function, this x minus 1 over x minus 1. We can probably simplify that a little bit, and I think we will. So we want to look at the limit as x approaches 1 of the function f, and then we want to look at f of 1. So what are these two quantities? I think it'll be helpful in this case to draw a picture. So this will be a graphical evaluation of this limit. What is this function x minus 1 over x minus 1? What does that function look like? Well, we can certainly reduce this thing. I mean, we can just cancel the fraction and get that this function is equal to 1 as long as x is not equal to 1. So just to leave this restriction out, this equality is false. This function is not equal to 1. It's equal to 1 everywhere except for at the point where x is equal to 1. So here's a picture, right? It's the constant function y equals 1, except for at x equals 1, we get a deleted point. So the question is, what is the limit? So the limit as x approaches 1 of f of x. What is that? Well, you can see when x is very close to 1, if I take an x right here and plug it into the function, I'm going to get a height or a y value of y equals 1. If I choose an x over here and plug it into the function, I'm still going to get a height of y equals 1. So no matter how close I get to 1, but not equal to 1, no matter how close I get to 1, whatever x I choose that's close to 1, when I plug it into the function, I'm still going to get a 1. So that says that all of my y values are very close to y equals 1 when x gets close to 1. So here's the answer to part A. The limit as x approaches 1 of f is 1. Part B asks, what is f of 1? Well, it's nothing. There's no dot anywhere at x equals 1. So according to this picture, according to this definition, f of 1 does not exist. I'm not allowed to plug 1 into this function. So the value at 1 has no meaning. So we can see the difference between limit and value. Here the limit exists, but the value does not. So make sure you're good on the difference between limit and value in this case. Okay. Let's have a look at another example. So in this case, I want to let f of x be this piecewise defined function, x squared minus 1 over x minus 1, when x is not equal to 1. And then we will define f of x to be 0 when x is equal to 1. And so we want to find the limit as x approaches 1, and then we want to find f of 1. So I think, again, the best thing we can do is to draw a picture, and then we can answer these two questions, no problem. So about this function f, if you can simplify, like factor and cancel, or anything you can do to simplify, that might be a good thing to try first. At least it is in this case. So in my piecewise defined function, I had x squared minus 1 over x minus 1 for the first piece, and I had 0 for the second piece. So how can you simplify that first piece? Well, you can just factor the numerator as x plus 1 times x minus 1 over x minus 1, and then the x minus 1s will cancel, and now I'm left with x plus 1 as long as x is not equal to 1. So again, to say that this function is equal to this function without the restriction x not equal to 1, that's false. X squared minus 1 over x minus 1 is not equal to x plus 1. It is equal to x plus 1 everywhere except for at x equals 1. So that's really important that we throw in this restriction. Now, I can rewrite my piecewise defined function then as x plus 1 when x is not equal to 1 and 0 when x is equal to 1. So this thing is very easy to sketch. So it's just the line y equals x plus 1, except we need to remove the usual point from the line and say that when x is equal to 1, the function is equal to 0. So that means I need to put a dot right here at 1, 0. So we've got the line, everything's good until we hit 1, then we have to drop down to this point abruptly, and then pick back up on the line once we're away from 1. So what is the limit as x approaches 1? Just by looking at the picture, we can see that when y gets very close to 1, when x gets very close to 1, the y value will get very close to the number 2. So we can see that the limit as x approaches 1 of f of x is just 2. And then what is f of 1? Well, the height of the function, or we get a dot at y equals 0, so the value of the function at 1 is 0. Once again, we've got a situation where the limit as x approaches 1 is different than the value of the function at 1. So the limit is 2, the value is 0. Those two things are different. Later in the course, when we define continuity, that'll be the situation where limit and value are the same thing. So that's a very important concept. We'll talk about that later. But for now, please observe that limit and value can be totally different. Okay, here's our last sort of introductory example using the graphical method, just to get our intuition built up for what limit means. So here's another funny looking piecewise defined function. Again, it'll be helpful to draw a picture. So this is negative x whenever x is less than 1, and positive x whenever x is greater than or equal to 1. And again, we want to find the limit as x approaches 1 of the function f, and then we want to find the value of the function at x equals 1. That is, we want to find f of 1. So again, best thing to do, draw a picture, and then we can see everything that we need to see in order to answer these questions. So we want to find the value and limit at x equals 1 of this particular function. This piecewise defined function, it's negative x when x is less than 1. So here's that piece. Here's the line y equals negative x, and so we graph that to the left of 1. And then we want the line y equals x. So here's the line y equals x, and we want that to the right of 1. And again, at x equals 1, right, we do a solid dot on this piece, right, because x could be equal to 1 here. So when x is 1, we've got 1 comma 1 here. So what is the limit as x approaches 1? So here's how we can answer that. By inspection, as you move towards 1 from the left, when you approach 1 from the left, the y value gets closer and closer to negative 1. So that's 1. That's, I guess, the left-hand limit. We'll define that in a second. As I move towards 1 from the right, the y value that we get close to is positive 1. So we must get close to a single y value in order to say that the limit exists. So from the left, we get negative 1. From the right, we get positive 1. Those two things are different. So we don't get close to one single y value. Therefore, the limit does not exist in this situation, right? We're not getting close to a single y value, so the limit does not exist. So here's our first example where the limit does not exist. Maybe it exists, maybe it doesn't. Our first two examples, the limit did exist at 1. In this example, the limit does not exist at 1. What about the value of the function at 1? Well, come over here, inspect the vertical line at x equals 1. Where do we run into the function? Well, we don't run into the function here. That's an open circle, right? There's no function here. We do run into it here. So we can see that the value of the function at 1 is positive 1. So in this case, the limit does not exist, but the value does exist. So maybe we want to write down a definition of left-hand limit and right-hand limit, and then a theorem to say when a limit does or does not exist.